On behalf of all of us, Conference Organizing Committee, it is my great honor to officially open 62nd International Scientific Conference of Physics and Natural Sciences, Open Readings 2019, here in Vilnius.
Dear participants, dear young researchers, colleagues, our honorable guests, we are really delighted to see here the full audience of young researchers in this heart of Sunrise Valley. Today, our chairman of the conference, Edvinas Kliūtis, is now at the inauguration ceremony of Gerard Mourou. As you all know, Gerard Mourou, in previous year, received his Nobel Prize in Physics. And today, he will become a foreign member of Lithuanian Academy of Science. And it's a big and crucial moment, I think, for us, and we are really happy that it happens during the Open Readings Conference. So now, before we go into briefly of program details and technical details, I would like to invite here the Dean of Physics Faculty of Vilnius University, Professor Juozas Šulskus.
Hello, dear guests, dear participants of the conference. Welcome to Open Readings 62, it was written in invitation. In earlier times, in my students' times, it was a conference, scientific conferences, Students' Scientific Association of Physics Faculty, and only during these 30 years, all of us and students especially, we became more independent, more free, and suddenly about 10 years ago we realized that it is not Students' Association Conference, it is open reading, it's faculty independent, it's absolutely governed by students and young scientists, and we are very, very happy about that because they can organize, they can have better contacts and more fast. They have contacts with many from scientists, well-known scientists from all the world, and can invite them to the conference. And another thing, we are still, as I said, conference became faculty independent, and faculty of physics and our neighbors, technology science, life science, are still allowed to support this conference, and we are glad to do this. Thank you for this possibility. So I would like to wish you a good staying in Vilnius University, and pleasant and useful work in this conference. Thank you.
Thank you very much. Now, I would like to invite the, let's say, owner of this building, the director of Center for Physical Sciences and Technology, Professor Gintaras Valušis.
So dear guests, dear colleagues, dear friends, it's my honor to welcome you here in the beautiful place and the most important event of the year, Open Readings Conference. So it's an event which allows us to share your knowledge, which allows to feel excitement of physics, feel shoulders of giants, as also the way to collect wisdom. So Confucius, famous Chinese philosopher and teacher, reveals 3 methods to get knowledge, to get wisdom. First, by reflection, which is noblest. Second, by imitation, which is easiest. And by experience, which is bitterest. So open reading is a place allowing to connect all these items. Every year with a larger scale and every year with a wide angle. So I wish you to share your knowledge and experiences. I wish you to feel this area with boundless curiosity and passion to investigate. So I wish you fruitful and illuminating time at beautiful city of Vilnius.
Okay, thank you very much for such inspiring talk. Yeah. Now we are going to into some of the details of the program. Yeah, it won't take long. Let's see. Yeah, as you know, it will take 4 days, and we will hear 8 lectures of invited speakers, which represent such countries as Australia, Denmark, Switzerland, United Kingdom, Germany, and France. And each day, between those 2 lectures, as you see, we will have the oral sessions, which will be given by students. And in the end of each day, we will have the poster session. Also, as you see, we have 2 coffee breaks, yeah, each day. So in the outside of this hall, on the left, yeah, we have the special coffee zone. So we encourage you to go and have your coffee during the coffee break. And the main, maybe, proposal, yeah, we want to encourage you to participate in social events. First of them happens today. As you see, Gerard Moreau is going to give the public lecture, which is called Passion for Extreme Light. It will happen at 5 p.m. at Life Sciences Center, so a building across the road, so nearby. Let's meet there today in the evening. And the next event will happen tomorrow in the evening. It's a discussion between scientists. And as you see, we are going to talk about scientific career, its personal ups and downs, and the living between them. So we all know about achievements, but we don't know what is behind that. Yeah? What does it truly mean to be a scientist? So a discussion will be between Jocelyn Bell-Barnell, Kishan Dalokia, Linas Vilchauskas, tomorrow at 5:30 in this hall. Yeah. Quality of the conference was ensured by our program committee, our scientific committee. Here is the list of people who have reviewed all of the abstracts. So this year we have broken the record once again because we received, yeah, almost 500 abstracts. It's really impressive. Yeah, so the list of the speakers and the presenters is really impressive, as well as the talks and topics about which we are going to talk during the conference. So we have the representatives from 20 countries, not only from Europe, yeah, but from Asia too. It's really nice. Big thanks for my colleagues, for professionals, for their professional, passionate work. Yeah, this conference is happening now. So here is the list of those 16 people for whom we should be thankful that Open Readings this year is really a huge event. Yeah, at the end of this week, yeah, we have the awards ceremony. So the best oral presenters, best poster presentations will be nominated and awarded in different areas. Also, we have one additional contest. It is called Photo Contest. So this year, it's something new. It is organized by Center for Physical Sciences and Technology. The main idea is to capture the moment during the conference, maybe during the coffee breaks, during the presentation, maybe some selfies with your friends. And when you should post it on Facebook and hashtag FTMC, hashtag Open Readings. And on Friday, Center for Physical Sciences and Technology will nominate the winners of this category. So here is the list of organizers, student chapters that are involved in the organization process. And here is the list of our sponsors for whom we are really thankful. So in the end, I would like to remind that Open Readings has a really long history, over 60 years. And it began from invitation of the local stars, from the global superstars. Now even we have the Nobel Prize laureates. So it became like an opportunity of a lifetime to meet a person, a scientist, face to face, like it will happen today. So receive the brief of newest scientific discoveries, enjoy your conference, and make unforgettable memories. But in the end, we would like to begin this contest to commemorate the beginning of open readings. We would like to take our first selfie with audience, which will be put on the open readings page today. So, smile all. Yeah. Okay, almost all. Yes, yes, thank you very much. So, now we are going to invite the director of Institute of Photonics and Nanotechnology, Professor Saulius Juršienis.
Good morning, ladies and gentlemen. It's a great honor for me to introduce you Professor Ifor Samuel from St. Andrews University. He received his PhD and master degrees from Cambridge. Then he continued with postdoc position in French Telecom. Afterwards, he moved to Durham to start organic semiconductor and semiconductor studies. And he established his own group. And in 2000, he moved to St. Andrews and established Organic Semiconductor Centre. He is now the leader of this world-known center. The main topics of this group is well known. It's light-emitting, organic light-emitting diodes. It's organic lasers. It's organic solar cells. It's organic sensors and biomedical applications. And the main property and main characteristic of this group is that it's based on really deep physical understanding of the processes going on in the organic semiconductors and devices. And well-known and recognized papers on exciton diffusivity and in organic semiconductors, on working of organic lasers, on development of second and third generation of organic light-emitting materials, as well as fascinating advances in applications of organic light-emitting diodes for healing cancer. I hope it will be shown in this presentation. And it's really, all these things makes the St. Andrews Group one of the world leader of organic semiconductor topics. So please welcome Professor Ifor Samuel, and he will present a talk, Organic Semiconductors Lighting Up the Future.
Okay, well, thank you very much indeed for that very kind introduction. It's a great pleasure to be in Vilnius and in Lithuania, which is very well known for its research in optics and many areas of science. And I'd also like to thank the organizers very much for the invitation to come to this conference. It's very attractive to me that it's a student-led and organized conference. So what I'd like to do over the next hour is to introduce you to the world of organic semiconductors and show you the many ways in which they can contribute to lighting up our future. So the work that I'll show was done at the Organic Semiconductor Centre in St. Andrews, which I founded and lead. and it involves many collaborations with engineering groups in Oxford and Edinburgh for the communications work, with Ninewells Hospital in Dundee for the medical work. And I just want to mention this is a very unusual photograph of St Andrews taken by Alex Thompson in my group. So it shows obviously the castle and the sea, and these are the northern lights. And then what's really exceptional about this photograph is that on that night, the sea was so calm that you can see a reflection of the northern lights and the castle in the sea. So I thought, as people living mainly at northern latitudes, you'd appreciate this, this photograph. So in case you're wondering, we're here on the east coast of Scotland, almost on the edge of the world, 800 kilometers north of London. Anyway, in terms of the talk, I'll give a substantial introduction to the field. It's about 20 slides, introducing light, materials, and then explaining about what organic semiconductors are and why they are interesting. And then after that, the main body of the talk involves looking at applications of them in medicine and in communications. So to begin with, I'd like you to think about light for a little while. So of course, light is very important. It enables you to see me, us to see the beauty of the world around us. For example, rainbows, sunsets. Of course, it enables us to study the universe, keeps astronomers in business, and these are Hubble Space Telescope images. So it's a very important topic. And in fact, there's no more important topic because, of course, it's light that supplies energy to the planet, which enables all of life to occur. Well, increasingly, rather than just observe light, we seek to control it. And so that's very important for communications. So, of course, pretty much all the data for the internet and telephone calls are carried by light in optical fibers. So we control light for communications. Of course, after sending information, you need to display it. So the light coming from a display to our eyes is ultimately how we get our information in the information age. Just on the right here is a different set of displays in the cockpit of a Boeing 747. So light's very important, but I want you to think as well about materials, because I would argue they're also extremely important. So if you think about it, advances in materials underpin much of modern civilization. So for example, having reinforced concrete, steel frame buildings and so on enable skyscrapers to be made. If you think about advances in metals, a very precise control of metals gives us, for instance, the jet engines, which mean that we now take intercontinental travel for granted. The very precise control of silicon gives us the whole of modern electronics. The very precise control of silica gives us optical fibers and the internet and telecommunications. And of course, the influence of materials is so great that whole eras of history are named after their materials technology. So I'll just introduce you to one particular class of material for now, and that's polymers. So polymers are organic materials, so they're generally made from carbon. And the word comes from the Greek, poly meaning many and meros, units. So polymers have many units. So schematically, the structure is some unit which repeats along a chain. Slightly more realistically, this is a little bit of polyethylene. So we have a repeating chain of carbon atoms. And I'd like you to think for a moment, why do we find plastics or polymers everywhere nowadays? So if you just think for a moment, and okay, I'll offer, as it's early in the morning, I'll offer the answers without actually asking you. So, unless anyone wants to. No. So one reason is there's a huge range of possible structures, and that leads to a huge range of possible properties and the possibility of changing the properties by changing the structure. So I can have a soft polymer for clothing or packaging. I can have a strong polymer for the cooling fan in my car, and many things in between. And so that's one major reason they're everywhere. And the other major reason is that they're simple to manufacture and to process, simple to shape and mold, for example. But if you look in a textbook, it will very likely tell you that all plastics are electrical insulators. And that's not quite true. So the class of materials that I work with are semiconducting polymers and related materials. So you can actually have a plastic which can conduct electricity, which can be a semiconductor. And that's because in certain plastics, you can have a difference in their structure. So these are called conjugated polymers. So conjugated means that the chemical bonding is a pattern of alternating single and double bonds. So the simplest example is shown here, polyacetylene. And because of that difference in the bonding, effectively there are spare electrons which can move around. If we're a little more precise about that, of the 4 carbon valence electrons, 1 is in a p orbital above and below the plane of the molecule, and these neighboring p orbitals overlap. And so you have overlap of atomic orbitals, and this leads to the formation of bands. And so that's just the same as where the bands come from in silicon or gallium arsenide. And then at various levels of complexity, as I say, you can either think there are sort of nearly free electrons sloshing around so it can conduct, for a very qualitative explanation. If we want to be a bit more precise, then there are 2 of these electrons per repeat unit of the molecule, and so that leads to a filled band and semiconducting electrical properties. So you can have polymers which are semiconductors, you can have semiconductors made from organic materials, and so that's a very important advance. And so Alan Heeger, Alan McDermott, and Hideki Shirakawa won the Nobel Prize for Chemistry in 2000 for their work in this direction. Now, originally the field was really studying them as conducting materials, but as I'll show you, and as you may be aware, semiconductors are actually much more interesting. You can do more things with semiconductors, and even more with organic semiconductors. So, as I say, the key point made so far is that you can make semiconductors from organic materials. They're conjugated molecules. And then this is very interesting, because this gives us a whole new class of semiconductors, gives us a whole new world of semiconductor physics to explore. These materials can be easy to process. You can tune their properties by changing the structure. They can emit light. They can be flexible. So they're shown here. So this is some of these materials under ultraviolet light. So you can actually have your semiconductor dissolved in a bottle, and you can paint or inkjet print or spin coat it to make working electronic and optoelectronic devices. And you can have a flexible film of them, and you can make all sorts of strange shapes of semiconductor. And so semiconductors are very important because we can make a whole range of very interesting devices from them. Okay, so transistors for logic, light-emitting diodes, solar cells, photodiodes or light sensors, and lasers are all semiconducting devices. And so what's very interesting is that we can now think about making such devices from these organic materials and benefit from the possibility of tuning the property of the material by changing the structure, having something that's plastic and therefore flexible rather than rigid and brittle as silicon is. So there are many differences, of course, between organic semiconductors and the and conventional inorganic semiconductors. So an inorganic semiconductor such as silicon is grown as a single crystal at around 1600 degrees, has to be incredibly pure, it's sliced up by a diamond saw. It's a superb material for high-speed electronics, but it's also a very energy-intensive material. Now we're working with materials, as I say, that are semiconductors dissolved in a bottle, and partly because of their lower dimensionality, their one-dimensional character, we have strongly bound excitons, strongly bound electron-hole pairs as the fundamental excitations in these materials. But as you can see, they emit light, and this is wonderful because, of course, right, it's beautiful to look at, it's useful, and the light they emit gives us a whole window on the physics of the materials. So in photoluminescence, that's where we shine light on the material and see what happens. Then if we shine light on, we'll excite an electron to a higher level, and we form a bound electron-hole pair. So the key point is at room temperature in an organic semiconductor, the electron and hole are strongly bound, unlike silicon or gallium arsenide. And so the physics of excitons is very important in these materials, and we study it extensively. We explore questions like how do the excitons diffuse? How do they interact with one another? Can you get a Bose-Einstein condensation of these excitons? Now, you can also generate excitons electrically. So then you can get light emission as it decays. You can generate them electrically. So now inject an electron over here and a hole over here, and they can form an electron-hole pair. And again, that can emit light. And clearly, if you've got electrically generated light emission, then that's very interesting as a potential display technology. And so this is a process which happens in organic light-emitting diodes, which are now quite widespread. So I mentioned we're very interested in understanding and studying excitons in these materials. Of course, we use lasers, yes, quite a lot of Lithuanian lasers, as it happens, from light conversion to study the dynamics of excitons. And so here are some of the lasers, not quite as clear on the screen as on my computer. But anyway, we use short pulse lasers of various colors to excite the materials. And we study the laser dynamics with many instruments and on many time scales, but this includes with street cameras, which give beautiful data like this. So this is a spectrum going across the screen, and it's time going down the screen. And so we can measure the whole spectrum as a function of time to learn about the underlying physics of these materials. So we very much like doing that, but we also quite like to use that understanding to explore and develop applications, which will be a substantial part of the talk as well. I should also mention very briefly, for our spectroscopy, we don't need very intense lasers, but we do want to be able to have any color we want of the laser. And to do that, we therefore do in fact use intense laser pulses and nonlinear optics to change the color of the wavelength. And so our lasers do use chirp pulse amplification, and of course we'll hear, I expect, much more about that from Gérard Moreau this evening. So as I say, you can generate light electrically. So in the simplest case, you just have a layer of the organic semiconductor in between two contacts. You apply a voltage, it's just a few volts, and you inject electrons from one contact and holes from the other contact, and they can meet up and make light. So that's illustrated here. and now there are very interesting OLED displays and lighting. So basically you can have curved displays. So this is a Samsung prototype. Now they're launching a flexible display in a commercial product. So you can have flexible displays. You can also make unusual shapes of displays, such as curved displays, as illustrated here. So very distinctive displays, and also because the display itself generates the light, you get very, very good contrast and viewing angle compared with a liquid crystal display where you have a backlight and something modulating the light. So the direct light emission gives you a much more pleasant and vivid display. And if you have a Samsung mobile phone, it's very likely it has an OLED display in it. So in the next few slides, I'll just give you a quick tour of some different areas of organic semiconductors. I've just mentioned OLEDs. I'll just let you know in that field, one thing we did many years ago working with Paul Byrne, who was in Oxford at the time, now at the University of Queensland, was to develop a whole new architecture of molecule, a whole new shape of molecule, light-emitting dendrimers. So these are highly branched molecules where different parts of the molecule do different things, and this enabled us to make, at the time, the most efficient solution processed organic light-emitting diodes in the world. Nowadays, I do lots of work exploring a different emission process of thermally assisted delayed fluorescence. So just going on and touring these different devices, you can also use these materials to make solar cells. And here this is very interesting because if you're making solar cells from plastics, as I've said, they could be flexible. That means you have the potential to make them by roll-to-roll processing, and so the potential to mass produce them at quite modest cost. And cost is a major consideration in the take-up of solar technologies. More than that, it's also interesting because the energy of manufacture matters for solar cells. So the energy of manufacture by the sort of process I just described with these materials is dramatically lower than for inorganic solar cells. So far, their efficiency is lower than the best silicon solar cells, though it's better than amorphous silicon solar cells. So there is potential for organic solar cells. As we're doing a quick tour of organic and semiconductor devices, I'll mention there are lasers. So far all organic semiconductor lasers are optically pumped. And so here's a photograph of one of them in our labs with a very distinctive cross-shaped beam shown here. So we do a lot of work on organic lasers, but it's not today's topic, but I thought you'd like to see the picture and be aware it happens. So in terms of the Organic Semiconductor Centre in St Andrews, we bring together physicists and chemists to make materials, but really to know what materials to make, you need to understand the materials. And so we do work on developing measurements that guide us towards what materials should be made. So at the heart of the group, basically we're studying the photophysics, light-induced physics of the materials. But we quite want to relate that to devices. So we also make devices, namely lasers, organic LEDs, and solar cells. And furthermore, we explore applications in sensing, communications, and biophotonics. So today I'm going to tell you about work on these two areas of application in the rest of the lecture. So, as I say, the plan for the rest of the lecture is I'll tell you about two applications in the domain of biophotonics, and then one in invisible light communication. Why don't we pause for a moment so that people standing over there, if you like, could come across to the other side of the lecture theatre, and then there'll be room for more people if they arrive during the talk. And if you did arrive late, I can do a very quick recap. It's that we can have semiconductors made from organic materials which are processable and flexible. So let's go on and look at some of the applications they enable in biophotonics and communications. So let's think for modern medicine for a moment. So some trends in modern medicine are towards continuous monitoring. So increasingly we'd like devices which can measure things in medicine all the time. So for example, traditionally, if you might have high blood pressure, you might go to your doctor and he'd take one measurement of your blood pressure, maybe decide it's high, and maybe give you a treatment. And, you know, maybe your blood pressure is actually doing this, going up and down and up and down and up, and you go to the doctor and he gives you a treatment, and the treatment doesn't actually work, so your blood pressure's still going up and down and up and down, and you go back and he measures it when it's here, and so he thinks the treatment's working, and then maybe it goes up again and kills you. So that's not what you want to happen, right? So you would like to be able to measure important physiological indicators continuously. And if you measure continuously, you're going to need wearable devices. And so there's a trend in medicine towards, let's say, wearable, ambulatory, meaning you can walk around during the monitoring or the treatment. And clearly, if you're doing continuous measurement, it needs to be non-invasive. You can't take a milliliter of blood out every 5 seconds for your continuous monitoring, or you'll defeat the point. So these requirements actually align rather well with the sort of ground I've been setting, because conjugated polymers and other organic semiconductors enable us to make thin and flexible devices that could therefore be used for monitoring and treatment. So about the next 10 slides are about skin cancer. So skin cancer is a major and growing problem. So even in Scotland, about 15% of the population get a skin cancer during their lifetime. In America, it's around 40%, and in Australia, 75%, which if you think about it means actually pretty much all white Australians get a skin cancer during their lifetime. So it's a significant and growing problem. And then there are various treatment options. Obviously, you can cut out a skin cancer. There are creams, but they leave horrid weeping wounds for months on end. For very small minor skin cancers, you can use cryotherapy, but that's still a cold burn. If you do nothing, that's also bad. So this is a neglected basal cell carcinoma. It just grows and grows, and eventually it erodes bone, which is clearly not something you want to happen. So there is an alternative so I just mentioned most skin cancers are not melanomas. So about 99% of skin cancer is non-melanoma skin cancer, fortunately, and that's what we work with. So this majority that isn't melanomas. And you can treat those another way by photodynamic therapy. So this is where you use a light-induced chemical reaction to kill the tumor. So what you do is you apply, you apply something naturally occurring aminolevulinic acid or something closely related to it as a cream, and you wait 3 hours, and basically the body metabolizes that to a porphyrin, protoporphyrin 9, and basically that is then made into hemoglobin. But cancer cells don't make hemoglobin, so they accumulate the porphyrin. And so after 3 hours, we've got the following situation. So this is the skin cancer and skin under normal light. And this is it under ultraviolet light. So under ultraviolet light, you can see a sort of a red fluorescence from the porphyrin that's formed in the tumor, and a blue autofluorescence of the skin around it. So this is really fantastic in the sense we've got a very strong selection for the tumor. So in any cancer therapy, you want a very strong selection. And then we shine on light, and it causes a photochemical reaction which generates reactive oxygen species which kill the tumor. So that's photodynamic therapy. So if you think about it, that's a light-based way of treating a skin cancer. And so it's much gentler, leads to a better cosmetic outcome. It's not perfect, so this is it being implemented at Ninewells Hospital. I should say I've worked for many, many years with Jimmy Ferguson and Sally Ibbotson at Ninewells Hospital on developing this, and they've been fantastic colleagues for the development of a new treatment in medicine. So here it's being done at Ninewells Hospital with a diode laser for illumination. Fairly typically, the patients are relatively old. Not shown here, but present will be a nurse or technician talking to the patient, partly because it's partly because it can be painful to distract them. You can see there are issues of eye safety in this implementation. And basically, you can use LED sources. Again, the commercial ones are very big machines. And so we wondered if there was a better way of doing this. But I'll just show you a picture that convinced the dermatologists that photodynamic therapy was the way to treat things. So basically, this is a large, complicated skin cancer. And actually, the plastic surgeons didn't want to operate on this because they thought it was too difficult for them. So they sent it over to the dermatologists. And after 3 cycles of photodynamic therapy, this was the outcome for this patient. So you can barely see where it was. So it's this is a remarkable outcome from photodynamic therapy in general. And then our contribution has been to work towards making the light sources ubiquitous. So in the past, there were only 7 hospitals in Scotland that could give photodynamic therapy. So although it's a treatment I would want for one of these conditions, it's not so widely available. So with Jimmy Ferguson at Ninewells, we had the idea of making a wearable light source for photodynamic therapy of skin cancer. Okay, so here's a prototype. So it's an organic light-emitting diode, 2 centimeters in diameter, but really in the form of a light-emitting bandage or sticking plaster. And so basically the idea is you would apply the cream, you would apply the light source, and you could walk around during the treatment, you could throw away the light source afterwards, so you could give an ambulatory treatment and have a better way of treating skin cancer. So over many years we've tried this out. So the general idea, just to recap, is you'd apply the cream, then you'd apply the device, then you could do your day's work, engage people in conversation at the photocopier, and then potentially throw the device that had been in contact with your skin away. So we've done various scales of trial on this. So in the original pilot trial, here's one case. So this, of course, a very small basal cell carcinoma, and this is it after 2 cycles of treatment. So you apply the light for 3 hours. The 2 treatments would be about a month apart. The photograph would be at about 6 months follow-up. So as you can see, you can barely see where the lesion was. So again, that's a very good cosmetic outcome. And if you think about it, you get skin cancers due to the sun, so you get them in places people can see. And in some countries, you get, you get quite a lot of them, and so it does matter what it looks like. And if you go to the States where photodynamic therapy isn't used, you do see some people with quite large parts of their face very heavily scarred because they've had multiple skin cancers removed. So this is a very good cosmetic outcome. Then there's some indication of another advantage. We use a lower light intensity for a longer time. We're trying to do a photochemical reaction, so we deliver the same dose of light, so that's fine. But certainly in our preliminary work, we found that there was much less pain from using the ambulatory device, the wearable device, and we believe that's because we're using a lower intensity for a longer time. And so, you know, to summarize, so there's a much larger trial running, but in the current trial so far, the treatment's as effective as conventional photodynamic therapy with a laser or a big light source. There's some encouraging signs on pain. And really this is potentially very significant because you can do an ambulatory treatment, you can move around during the treatment. It means that ultimately you'd be able to give this treatment from a family doctor or at home, has the potential to be low cost and gives all the usual benefits of photodynamic therapy in terms of a good cosmetic outcome. And so the International Photodynamic Association very kindly gave me and Sally Ibbotson a prize for this work, and I'm showing that basically just to show its main impact on the photodynamic therapy community. So I formed a spin-out company to develop this further, and then of course in spin-out companies things take on a life of their own, and in the commercial world everything is more beautiful. So here we are. This is a related device. So I've talked about a wearable light source for skin cancer treatment. The company also has a device of the same idea, but it's wearable blue light, and it's for treating acne. And so, yeah, so then this is how it advertises it. Unfortunately, I wasn't in the office the day she visited. And I say unfortunately because I wasn't able to check how bad her acne was before she arrived. But anyway, so things very beautiful in the commercial world. Physicists aren't very happy with pure light as a notion, but anyway, so there's a skin cancer product sold by Ambicare Health, and then there's also this acne treatment called Luster, which is on the shelves of 200 Boots stores, which is the main, biggest pharmacy chain in the UK. So that's wearable light sources for treatment. What about for measurement? So we've been working on making a muscle contraction sensor. And if you think about ways of measuring muscle contraction, one way of doing it is actually to use electrodes. And really, if ever you have electrodes, in the end, you need little needles to make contact. And then there's an immune response to the needles, which coats them and makes them insulating. So it's quite hard to do long-term measurement effectively electrically. So an optical measurement would be much nicer and is possible. So basically, so obviously muscle is quite fibrous, and that means it scatters light differently in different directions. So maybe we'll think about my bicep, the fibers running along here, and basically light is scattered differently in this direction from this direction. And that difference changes when the muscle contracts. And so we can measure that. So basically, you can have a light source, and then you could use 2 photodiodes to measure the scattering this way, a different 2 photodiodes here and here to measure the scattering that way. And then you could take the difference of those signals to learn about the extent of contraction of the muscle. Now, if you're going to do that, you'd clearly want a flexible device to do that, and so organic semiconductors are the natural way of making that. And so here's a flexible organic light-emitting diode. So we used a very simple, in fact, old material as the light emitter, but it's important to keep in mind for this purpose it was perfectly adequate, so you don't always need to multiply your difficulties by using the newest and fanciest material. You can use an old material if the performance is good enough, and we could make flexible light-emitting diodes. And then we made flexible photodiodes, and we assembled them together into a wearable device. And then we used that to measure contraction of the bicep. So I'll just mention that 2 sorts of contraction of muscle. One is an isotonic contraction, which is basically doing this. So that's a constant force contraction. There's also an isometric contraction. So that would be like now where I'm lifting this table with this muscle. So it's using energy and it's tense, but it's not actually moving. So constant length isometric. So those 2 sorts of contraction. And then we took this sensor and we looked at its output, taking the difference of light parallel and perpendicular. And very interestingly, we did different contractions, and basically we get a different sign of signal for an isometric and an isotonic contraction. So that's very useful. It's an extra piece of information for free, in a sense. And so basically, we could use that to detect different motions. So it turns out, so of course, this is an isotonic contraction. It turns out if I then turn my wrist, there's some isometric contraction of the bicep as I turn my wrist. And so in the next slide, and hopefully I'll persuade the video to work, this is my student Shuben, who was working on this device, and he'll lift and lower his arm. And okay, so one of the possible reasons for doing this would be to have a sensor which could control a prosthetic limb. So we didn't have any prosthetic limbs lying around the department, but we did have a robot arm, so we used it instead. And so you'll see Shuben lift and lower his hand, and then he'll twist his wrist, and the robot will follow. So basically, he's wearing this device on his bicep, and there's a robot arm programmed to follow the signal. So here it is. So he lifts his arm, he lowers it, the robot follows, then he twists his hand, and the robot copies that. And this is all using the signal from this wearable sensor using organic optoelectronics. So it's a very encouraging result, and it shows it has the potential to control a prosthetic limb. It got quite a lot of press attention, as you might expect. And so in the middle is Elena Kulik, who worked on the project as well. And Ashu Bansal in my group, who did a lot of work on the project, his wife was always asking him why was he wasting all his time at the lab, all those hours, whilst I think his brother was in a well-paid job in information technology, and finally, when he got interviewed by the Times in India about this work, she finally said he could spend as long as he wanted in the lab. So we'll go on to the last section of the talk, which is about visible light communication. And so there's quite a serious problem coming, which is essentially we're running out of radio frequency bandwidth. Okay, so data is growing and growing and growing, but the electromagnetic spectrum isn't. It's fixed. What's the radio frequency is fixed, and we're running, we're making cleverer and cleverer use of it, but we're running out of radio frequency spectrum. And so if you try and use your mobile phone to browse the internet in a stadium, you'll be very aware of this. So, so basically, that's a problem, but alongside that, increasingly we have solid-state lighting all over our buildings. And so there's a possibility in the coming years to use lights to deliver information as well, to supplement Wi-Fi with light. So the notion is that smart devices, computers, cell phones, and many other things would get data from light sources that are modulated, thereby giving far more bandwidth for communication. And so this field is sometimes called Li-Fi. So we've been working on that with the people noted here, Dominic O'Brien in Oxford, Harold House in Edinburgh is a pioneer of it, and the small inorganic LEDs are from Martin Dawson at the University of Strathclyde. So the way that this works, of course, is like in any communication system, you have a transmitter and a receiver, and you modulate the light. So you encode information on it, for example, by turning it on and off very quickly, or you could modulate some other property like the phase or the frequency. And then if you think about this, in a white light-emitting diode, you in fact have a blue LED made from gallium nitride, and then you have a yellow phosphor, and that converts some of the blue light to yellow, and the combination of blue and yellow is white, and that's what makes it white. But phosphors are really slow. So a phosphor has an excited state lifetime of many microseconds often, and so you can't turn that source on and off very fast and send information very fast. So that's a problem. So I've called that the phosphor bottleneck. So then the question is, how do organic semiconductors help with this? And so basically it's that they could potentially be used to replace this wavelength converter with something much faster. So if we think about the requirements for that for a moment, we've got our blue LED emitting light at 450 nanometers, and then we want to convert that to white. So we need a material which absorbs at 450 nanometers. We want it to have a very high efficiency of light emission, but we also want it to have a very short excited state lifetime. And that actually means then that we need a very short rate of lifetime, and it turns out that conjugated polymers are very strongly absorbing, therefore very strongly emitting with very short lifetime. They're exactly what is needed here. Clearly we want emission across the visible, and it does need to be reasonably photostable. So if we look at some candidate materials, so these graphs are all, this graph is showing photoluminescence as a function of time, or log of photoluminescence as a function of time. And for this graph, we want a fast decay. So the existing phosphors here, it's very long lifetime. That's very bad for this application. So you might think a 2.6 quantum dot would be a good idea. So it is a bit better, but it's still not great. So we explored various star-shaped organic semiconductors, such as this molecule. So that's a lot better. So it's going in the right direction. But you can get to even shorter lifetimes with high efficiency by using suitable conjugated polymers. So as I say, in this graph, you want to have the shortest lifetime possible. So these are very good, and so conjugated polymers are very interesting for doing high-speed color conversion for communications. So I'll show you some results of communication by this approach. So let me just explain a key thing in communication is the bandwidth of the channel. And you measure that by basically, you have your transmitter, you have your receiver, you put a signal on the transmitter, and you keep increasing the frequency, and you measure the size of the signal you get at the receiver. And basically, as you go to higher and higher frequency, the size of the signal you receive eventually goes down, and when it reaches half its initial value, electrical engineers call that the bandwidth. So now we're measuring bandwidth in this graph, and so we want the bandwidth to be as large as possible. We want this roll-off to be as slow as possible. And so now you can see this is a conventional phosphor, so it's terrible. The star-shaped molecule is better, and the polymers are much better still over here. So again, the polymers show a major advantage. And then if we go on and actually send data, so we have electrical engineering collaborators in Oxford who do this. So when you're testing a communication system actually sending data, what you do is you send the data faster and faster and faster, and you measure the number of errors. So the faster you go, the more errors you get. So this is a graph of the bit error rate as a function of the communication rate, the data rate. And then there's an acceptable level of errors, which is shown by the line here. That's the maximum amount you can very simply correct. And so basically, we've got our blue LED and our yellow color converter, and we're making white, and we're sending data at around 1.5 gigabits per second. So that's a world record for white visible light communication. So we're quite close to the end now. I'll mention very briefly, there is an issue on the receiver side in communications. How do you make a detector that is both very fast and very sensitive? Because usually if you have a small detector, it's fast, but it's not sensitive. We've developed a solution to that problem using, we call it an optical antenna. It's basically a fluorescent concentrator. So we absorb light over an area. The light goes very quickly to the edge, and we can have a small detector on the edge. And this is quite an interesting device that is fast and sensitive and gives large field of view. But don't have much time to talk about it. But to kind of sum up on organic semiconductors for visible light communication, so we can use them as very fast color converters. Potentially we could make directional sources. We use them as optical antennas for receivers. We have made receivers from organic solar cells which both receive data and generate power at the same time. So it turns out in the end there are many possibilities for organic semiconductors in this emerging field of Li-Fi. So I've got 3 slides to go. So to sort of conclude, I hope I've shown you that organic semiconductors are fascinating materials, processable, tunable, optoelectronic materials that enable a whole range of device to be made. They have very interesting underlying physics, so when we understand that, it enables us also to use their distinctive properties to develop new applications. And so I've shown you today some of these application areas: skin cancer treatment by photodynamic therapy, the wearable muscle contraction sensor, and visible light communication. Of course, it takes many people to do this much work, so I'm very grateful to the members of my research group, pictured in the department here. And finally, I just want to mention that if you're interested in this field, then after you've been to the optical probes meeting here in Vilnius this year, you should come to the ICSM in Glasgow next year. So the ICSM is the largest organic electronics conference in the world. It's also one of the longest running ones, and it's in Glasgow in July next year, and Peter Skabar and I are running it, so I'd encourage you to come along. But for now, I'll finish there, and thank you for your attention.
Thank you, Samuel, Professor Samuel, for a really fascinating talk and for showing us new directions in organic electronics. So now we open discussion. Are there any questions in audience? Yes, please.
Go a bit off track, but I currently work a bit with photodynamic therapy as well, but not with skin cancer treatment, but with endoscopic treatment. So basically the idea is the same. The photosensitizer is administered via endoscope, and then you have a laser that induces the photochemical reaction. So, yeah, right. So could you maybe provide some insights as to how organic light-emitting diodes can be used there? What might be the advantages, or is it not worth using?
Sure. So the question was about, could you also use organic light-emitting diodes for photodynamic therapy of internal cancers? So photodynamic therapy also treats internal cancers. We've worked on skin cancers because they're on the surface. It's easy to get light to them. So basically, then, for an internal cancer, it's kind of conceivable, but I think suddenly most of the advantages of the organic light source go away. So we're using a lower intensity for a longer time. If you're working on an internal cancer, often your patient has been cut open under general anesthetic, so they're not going to feel any pain. And the critical issue is how quickly you can deliver the light. If you're using an endoscope, you know, a laser may couple into the fibers very effectively. So it may well be that lasers are the right light source for the internal cancers. There would be a very interesting possibility of implanting a light source and having a completely different approach. The key problem there is the power. So although the light sources are small, you need to get power to them. So these would be the considerations to think about, and we can maybe continue the discussion over coffee. I should mention you can do other things with, many other things with light and with photodynamic therapy. So we are looking, for instance, at killing bacteria with photodynamic therapy. So that would be a nice extension. But I'd be happy to discuss it.
Thank you. Other questions? Yes, please.
Hi. For communications, why do you need to convert light? Why can't you use blue light? I did not get it.
Yeah. So okay. Well, if you want to use if you want a dual-purpose infrastructure where your light bulb is also the source of information for communication, then it will be white light, right? If you want to actually use white room lights for communication, then you've got to deal with white light, is the first point. So if you put in separate blue lights, you could communicate with those, but then it's a separate infrastructure. So, or maybe your question was, why couldn't you filter out the white light and just use the blue light?
So I did not get, so if you would use the bulb, so you would get the light coming in and out, and how that would affect our feeling? So why do you have to use the same light for communication and for lighting?
Well, if you do, it's one set of infrastructure. So remember, the eye only sees fluctuations slower than 50 hertz, and we're seeking to send a gigabit per second. Okay, so the modulation is going to be many orders of magnitude faster than you can see, and in any case probably wouldn't be from 100% to 0%. It would be a much smaller thing. So that's the main reason. There is a further bit to your question. So why don't you filter out the white and just use the blue? That is possible, and it does work, but then you've thrown away quite a lot of light. And in communications, your channel capacity depends on your signal-to-noise ratio, so throwing away the light then becomes a restriction.
Yes, thank you. Other questions?
This one.
Yes?
So just a simple question. You said you don't have to go from 0 to 100%. So what is the predominant noise sources in your in the communication? You said you have an acceptable error rate. What causes the errors? Is it just not? Is it photon shot noise, or is it something else?
Let's see. So I mean, in some sense, the way you test the communication rate, you just stress the thing until it doesn't work. So from an engineering point of view, I guess one doesn't think about it very much. In some circumstances, it can be shot noise in the detector. In our case, I'm just trying to think, so actually you do much more sophisticated modulation than on-off keying. So you do a very, so the actual multiplexing used is an orthogonal frequency domain multiplexing, and in terms of it, as I say, ultimately shot noise in the detector, but I'm not absolutely sure, so it's maybe more a question for the electrical engineers.
Thank you. Yes?
Is it still possible to sense muscle contractions for overweight people? Because I see it quite difficult to deal with fat scattering.
Okay, let's see. Let me just have a look. I can't find any. So okay, we didn't have any overweight volunteers. So let me I'm just trying to think. So okay, I mean, yeah, I mean, all tissue is very strongly scattering. And so I guess we don't yet know what the limitations of the device will be, and we would have to try it. And I agree there, I agree there's a possible, at some point that will be a problem and the light won't reach the muscle. It's maybe not quite as bad as you think, because we currently have the light source in the middle, and each photodiode is 2 centimeters to either side of it. Okay, so we're trying to probe at depth. So we are effectively taking light from centimeter dimensions. So it may be possible, but we don't know unless we try it, I guess.
Any more questions? So let's thank the speaker again. And there are some presents from organizers.
Thank you. Right.
Wonderful
Thank you very
talk.
Okay, so now all presenters of the first oral session, please come and upload your